Imagine a laboratory at 3 in the morning. The lights are still on. The room is quiet. No crowd of researchers is gathered around the bench. No one is rushing between machines with a notebook in one hand and a sample tray in the other. But the laboratory is not asleep. A robotic arm moves a plate of samples from one station to the next. A microscope captures images. A sensor records temperature, pressure, color, fluorescence, reaction speed, and chemical change. A model reads the results. Another model compares them with earlier experiments. A third model searches through years of literature, millions of molecular structures, protein databases, climate records, simulation outputs, and code repositories. Then the system does something that, not long ago, sounded like science fiction. It decides what to try next. Not because a human wrote one fixed instruction for every movement. Not because the machine is simply repeating a recipe, but because the system is learning from the experiment. It proposes, it fails, it adjusts, it builds a better question. For most people, artificial intelligence still means chatbots. It means image generators. It means voice assistants, writing tools, search tools, and software that can create a summary or answer a question. That world matters. It has already changed how people work, study, build, and communicate. But inside science, something larger is happening. Artificial intelligence is becoming an accelerator for discovery itself. AI is being used to design new drugs, to model proteins not as frozen shapes, but as living moving systems, to discover new materials, to write and debug scientific code, to build climate and weather forecasts in seconds, to connect data, robotics, instruments, and hypothesis generation into autonomous research workflows. This does not mean the human scientist disappears. That is the wrong picture. It means the scientist gains a new kind of instrument. Not a microscope, not a telescope, not a particle collider, a reasoning engine, a hypothesis machine, a mapmaker for complexity. And if there is one scientific trend that defines 2026, it may be this. AI is moving beyond chatbots. It is becoming the main accelerator across the scientific frontier. This is VTM Podcast. I am Ralph Clayton, and today we are talking about the moment artificial intelligence stops being only a tool we use to talk about the world and becomes a tool we use to discover how the world works. Let us begin with the central idea. Science has always advanced through instruments. The telescope extended human sight into the heavens. The microscope extended human sight into the hidden world of cells, bacteria, and structures too small for the naked eye. The spectroscope allowed scientists to read the chemical signatures of stars. The particle collider allowed physicists to probe the deep structure of matter. The genome sequencer opened the language of inheritance. The supercomputer made it possible to simulate weather, plasma, molecules, galaxies, oceans, and biological systems. Every major instrument changed what humanity could observe. But AI is different in one important way. AI does not only expand what we can observe, it expands what we can search. It can search chemical space, protein space, genetic space, material space, climate possibility space, experimental design space, the literature of all prior science, the shape of possible solutions. That is why AI for science is not just another technology trend. It is a meta-trend. It sits underneath many other trends and accelerates them. Drug discovery becomes faster because AI can help propose molecules and predict interactions. Protein engineering becomes faster because AI can design new binders, explore movement, and model conformational landscapes. Climate science changes because AI can generate fast forecasts and help analyze enormous planetary datasets. Materials science changes because AI can screen candidate compounds for batteries, semiconductors, catalysts, carbon capture, and clean energy systems. Scientific software changes because researchers can generate code, debug simulations, automate analysis pipelines, and connect instruments to models. And laboratory work changes because robotics, machine learning, and scientific reasoning can combine into systems that run experimental loops faster than human teams could manage manually. That combination is the real revolution. AI plus instruments, AI plus data, AI plus automation, AI plus human judgment. Not artificial intelligence as a replacement for science. Artificial intelligence as a multiplier of science. In this episode, I want to break that down into 5 major frontiers. First, drug discovery. Second, protein design. Third, materials discovery. Fourth, climate and weather modeling. Fifth, autonomous research workflows. Then we will ask the deeper question. What happens to the human scientist when discovery itself becomes faster? Because every major instrument changes not only what we know, it also changes who gets to know, who gets to build, who gets to decide, and who carries responsibility when knowledge moves faster than society can absorb it. Let us begin where much of the attention, investment, and hope is focused right now. Drug discovery. Drug discovery is one of the hardest problems in modern science. The public usually sees the final result, a pill, an injection, a therapy, a clinical trial headline, a breakthrough treatment. But behind that final result is a brutal process. You begin with a disease. Then you need to understand the biology. What target matters? A protein, a pathway, a receptor, a gene, a misfolded structure, a signaling cascade. Then You need a molecule that can interact with that target in exactly the right way. It has to bind strongly enough, but not too broadly. It has to reach the right tissue. It has to survive metabolism. It cannot be too toxic. It has to be manufacturable. It has to pass tests in cells, then animals, then humans. Most candidates fail. Many fail late, and late failure is expensive, slow, and painful. This is why AI drug discovery matters. It does not magically remove biology's complexity. It does not guarantee that a model's answer will work inside a living body, but it can change the search process. Instead of manually screening enormous libraries of molecules one at a time, AI can help predict which candidates are worth testing first. Instead of treating molecular design as pure trial and error, AI can propose structures with desired properties. Instead of relying only on static snapshots of biological targets, AI can help reason about motion, binding pockets, off-target risks, chemical modifications, and patterns hidden inside large datasets. The idea is simple to state. It is much harder to execute. Use computation to reduce wasted experiments. Use models to narrow the search. Use data to identify better starting points. Use learning loops to improve with every result. That is the promise. And it is why companies built around AI, first drug discovery, are receiving so much attention. The field is moving from demonstration to scale. From the question, can this work at all, toward the question, can this become a repeatable engine? That distinction matters. A single AI-designed molecule is interesting. A repeatable AI-driven discovery pipeline is transformative. Because if the pipeline works, you are not just discovering one drug. You are changing the economics of searching for many drugs. But we have to be careful. There is a common mistake in public discussions of AI and medicine. People imagine that if an AI can design a molecule, the drug is basically finished. That is false. A molecule is not a medicine until biology agrees, safety agrees, dosage agrees, delivery agrees, manufacturing agrees, and human trials agree. The body is not a clean simulation. The body is a living system, layered with feedback loops, immune responses, metabolism, cell diversity, genetic variation, environmental exposure, and unknown unknowns. AI can accelerate discovery. It cannot repeal biology. So the realistic story is not this. AI instantly cures disease. The realistic story is more grounded, and in many ways more powerful. AI compresses the early search process. It proposes better candidates. It integrates more data. It helps human scientists move through a larger possibility space with greater speed and precision. Think of it like this. Before AI, drug discovery often looked like searching for a key in a dark warehouse. You had flashlights, You had maps. You had expert intuition. You had teams of people searching row by row. AI does not simply hand you the key, but it can turn on more lights. It can identify which shelves are unlikely. It can learn from every wrong key. It can suggest keys that do not yet exist. And in a field where the warehouse is almost impossibly large, that matters. The next frontier is even stranger. Because AI is not only helping scientists search for molecules, it is helping scientists design and understand the biological machines those molecules interact with. Proteins. Proteins are the machinery of life. They fold. They bind. They signal. They transport. They build. They defend. They misbehave. They malfunction. They form structures, catalyze reactions, recognize invaders, and carry out much of the work that makes cells alive. For decades, one of biology's grand challenges was predicting a protein's a dimensional structure from its amino acid sequence. Then AlphaFold changed the public imagination of what AI could do in biology. It showed that deep learning could predict many protein structures with remarkable accuracy. A problem that once looked painfully slow and difficult became dramatically more scalable. But structure prediction was not the end of the story. It was the beginning of a new phase. Because proteins are not statues. They move. They breathe. They shift between conformations. They open and close. They expose hidden binding pockets. They change shape when they interact with other molecules. They exist not as one perfect frozen structure, but as an ensemble of possible states. That is where the next frontier begins, moving beyond static protein structures into conformational landscapes. That phrase sounds technical, so let us make it simple. Imagine you have a photograph of a dancer. That photograph can tell you a lot: posture, position, balance, the shape of one moment, but it cannot tell you the dance. A protein structure can be like that photograph: useful, beautiful, important. But life happens in motion. A conformational landscape is closer to understanding the dance. It is the range of shapes a protein can adopt, the probabilities of those shapes, the transitions between them, the moments when a drug, binder, or partner molecule might interact. This matters for medicine because sometimes the best binding site is not visible in the most common structure. Sometimes it appears only briefly. Sometimes the target is flexible. Sometimes function depends on movement. If AI can help model these landscapes more efficiently, it can reveal targets and mechanisms that static structure prediction alone may miss. The second major frontier is de novo protein design. De novo means from scratch. Instead of asking, what shape does this natural protein fold into? Scientists ask, can we design a new protein that does something we want? Can we create a protein binder that attaches to a disease-related target? Can we design a protein that blocks a viral entry mechanism? Can we engineer an enzyme that performs a useful chemical reaction? Can we build a biological tool that nature never evolved, but biology can still use? This is where AI starts to look less like a predictor and more like a designer. A protein binder is like a custom-made biological clasp. It is designed to attach to a target protein with high specificity. If scientists can design binders reliably, they can create new diagnostics, new research tools, new therapeutic candidates, and new ways of controlling biology. Again, caution matters. A designed protein that works in a computational model still has to work in the physical world. It has to fold properly. It has to remain stable. It has to avoid unwanted interactions. It has to perform in the messy environment of real cells and tissues. But the success rates are improving, and the direction is clear. AI is turning protein engineering into something more systematic, more scalable, and more creative. The important shift is philosophical as much as technical. For centuries, biology was mostly a science of description. What exists? What does it do? How does it work? Now biology is increasingly becoming a science of design. What could exist? What should we build? What function do we want? What structure would make that function possible? And what happens when the design space is too large for humans to explore without machine assistance? That is the key. Protein space is enormous. The number of possible amino acid sequences is beyond human intuition. Nature has explored only a tiny fraction of what is possible. AI gives scientists a way to navigate that vastness. Not perfectly, not without experiments, but better than blind search. And this same logic extends beyond biology. It extends into the physical stuff civilization is made from. Materials. Every technological era is built on materials. The Stone Age, the Bronze Age, the Iron Age, the Age of Silicon, the Age of lithium-ion batteries, the Age of fiber optics, superconductors, polymers, catalysts, photovoltaics, semiconductors, and alloys. Materials determine what civilization can physically do. If you want better batteries, you need better materials. If you want cheaper clean energy, you need better catalysts, solar absorbers, electrolytes, membranes, and conductors. If you want faster computing, you need better chips, better packaging, better thermal systems, and perhaps entirely new semiconductor architectures. If you want carbon capture, you need materials that can bind, separate, transport, or transform molecules efficiently. If you want fusion reactors, you need materials that can survive extreme heat, radiation, plasma exposure, and mechanical stress. The problem is that materials discovery is hard. The periodic table gives us ingredients. Chemistry gives us rules. Physics gives us constraints. But the number of possible combinations, structures, defects, phases, and processing conditions is enormous. A material is not just a formula. It is structure. It is synthesis. It is defects. It is grain boundaries. It is manufacturing. It is temperature, pressure, stability, cost, abundance, toxicity, and real-world performance. Traditionally, materials discovery has involved theory, experiment, intuition, simulation, and a lot of slow iteration. AI changes the search. It can predict candidate materials before they are synthesized. It can learn from databases of known structures and properties. It can suggest compounds that may have desired characteristics. It can help optimize processing conditions. It can connect simulations to experiments. It can help scientists prioritize which candidates deserve lab time. This does not mean AI can invent a miracle battery overnight. That is the wrong story. A model might identify a candidate material, but someone still has to make it, characterize it, test it, scale it, prove that it works safely and economically. But as with drug discovery, even narrowing the search can be revolutionary. Materials, science suffers from a familiar problem. The universe of possibilities is much larger than the laboratory capacity to test them. AI is a way of compressing that search. It becomes a filter, a guide, an imagination amplifier. In clean energy, this matters enormously. The climate transition is not one invention. It is a materials challenge across the entire economy. Batteries need cheaper and more abundant chemistries. Electric grids need better storage and transmission. Industry needs low-carbon cement, steel, chemicals, and fuels. Carbon capture needs sorbents, membranes, and catalysts. Nuclear and fusion systems need extreme materials. Electronics need more efficient architectures. Agriculture needs better sensors, fertilizers, and biological inputs. AI for science is not separate from the energy transition. It may become one of its accelerators. The same pattern appears again. AI becomes important wherever the scale of possible search overwhelms traditional methods. Drug space is too large. Protein space is too large. Material space is too large. Climate space is too large. Scientific literature is too large. Experimental combinations are too large. AI becomes the mapmaker when the territory exceeds human navigation. And there may be no system more complex, more urgent, or more consequential than Earth's climate. Weather and climate prediction are among humanity's most ambitious scientific achievements. To predict weather, you need to model a rotating planet with oceans, atmosphere, ice, land, clouds, radiation, vegetation, aerosols, storms, turbulence, and human influence. You need equations from physics. You need observations from satellites, buoys, aircraft, ships, radar, weather stations, and reanalysis systems. You need supercomputers. And even then, the atmosphere is chaotic. Small uncertainties can grow. Extremes are difficult. Local predictions can be hard. Climate change shifts the statistical background on which weather unfolds. Traditional numerical weather prediction is a triumph of physics and computation. But now AI models are entering the field. Some can produce forecasts very quickly. Some learn from massive historical weather datasets. Some can emulate expensive parts of physics-based models. Some can generate global forecasts at impressive speed. Some are being tested for storms, atmospheric chemistry, ocean waves, and high-resolution local prediction. The promise is enormous. If AI can produce accurate forecasts faster and cheaper that could help disaster response, agriculture, energy grids, insurance, shipping, aviation, water management, and climate adaptation, a faster forecast is not merely convenient. In a storm, speed can save lives. In a heat wave, earlier warning can protect vulnerable people. For a renewable energy grid, better forecasting of wind, sunlight, demand, and extreme events can improve stability. But climate and weather AI requires humility. The atmosphere is not a text document. It is governed by physics. A model that learns from historical data may perform beautifully under common conditions, but struggle with rare extremes, unprecedented combinations, or regimes altered by climate change. This is one of the central tensions in AI for science. AI can detect patterns faster than humans, but science needs more than pattern detection. Science needs mechanisms. It needs causal understanding. It needs physical consistency. It needs uncertainty estimates. It needs to know not only what the model predicts, but when the model should not be trusted. That is why the most realistic future is not AI replacing physics-based weather and climate models. The realistic future is as hybrid: physics plus AI, simulation plus learning, human expertise plus machine speed. Traditional models remain essential because they encode physical law. AI models become powerful because they can learn patterns, approximate expensive computations, generate fast forecasts, and identify relationships across enormous datasets. Together, they may transform climate science from two directions. First, by improving operational forecasting. Second, by helping researchers explore climate risk faster. Imagine needing to understand how a changing climate affects extreme rainfall in a specific region, or heat stress in a city, or wildfire risk near power infrastructure, or crop yields under different warming scenarios. traditional simulation can be expensive. AI tools may help downscale, emulate, accelerate, and analyze these scenarios. But there is a danger. If AI-generated forecasts become widely used without proper validation, uncertainty communication, and governance, people may overtrust outputs that look precise but fail in exactly the moments that matter most. So the future of AI climate modeling must be ambitious and disciplined. Ambitious because the need is urgent. Disciplined because a wrong forecast can cost lives. This is true across the whole AI. For science revolution, AI does not remove responsibility. It increases responsibility. Because when discovery speeds up, the consequences of error also speed up. That brings us to the next frontier. Scientific work itself, the laboratory, the codebase, the paper trail, the instruments, the research loop. Science today is inseparable from code. A biologist may write scripts to process sequencing data. A physicist may build simulations. A climate scientist may analyze terabytes of model output. A chemist may automate molecular screening. A neuroscientist may process imaging data. An astronomer may search enormous sky surveys. A materials scientist may connect computational predictions to lab measurements. In many fields, the bottleneck is no longer only collecting data. It is managing data, cleaning data, interpreting data, reproducing data, and acting on data. This is where AI coding assistants and research agents become important. At the simplest level, they help write code faster. They can generate boilerplate. They can explain errors. They can translate between programming languages. They can help build analysis pipelines. They can suggest statistical methods. They can create visualizations. They can help non-specialist researchers interact with computational tools. But the deeper shift is not merely faster coding. The deeper shift is integrated scientific workflow. Imagine a researcher asking a system to do this. Find the relevant literature. Extract key experimental conditions. Compare conflicting results. Generate a candidate hypothesis. Write analysis code. Run simulations. Design an experiment. Check whether the design has statistical power. Schedule the robotic lab. Analyze the output. Flag anomalies. Suggest the next experiment. That is not one tool. That is a workflow stack. And pieces of that stack are already emerging. Literature models can search and summarize papers. Coding models can help build pipelines. Machine learning models can analyze data. Robotic labs can execute experiments. Planning systems can choose next steps. Knowledge graphs can connect entities. Simulation tools can test possibilities before lab work. This is where AI for science becomes not just a model, but an operating system for research. We should still avoid hype. A model can hallucinate. A summary can miss context. A generated citation can be wrong. A code suggestion can contain subtle bugs. An automated analysis can produce beautiful nonsense if the data are flawed or the assumptions are bad. So the human scientist remains essential, but the role changes. Instead of manually performing every step, the scientist increasingly becomes a designer of workflows, a judge of evidence, a critic of models, a curator of assumptions, a strategist of discovery. This is not entirely new. Good scientists have always managed instruments, teams, methods, and interpretation. But AI increases the number of possible actions available at each step. It gives the scientist more leverage. That leverage is powerful and dangerous. Powerful because a small team may accomplish work that once required much larger infrastructure. Dangerous because a poorly supervised system may produce results at scale that are wrong, biased, irreproducible, or unsafe. This is why research integrity becomes central in the AI era. We will need better provenance. Which model generated which hypothesis? Which version of the data was used? Which code was machine-generated? Which parameters were changed? Which experiments failed and were not reported? How was uncertainty estimated? Can the result be reproduced by another group? Can the automated workflow be audited? The future laboratory may be faster, but if it is not transparent, it will not be trustworthy. And that brings us to the most cinematic version of this entire trend. The self-driving lab. The phrase self-driving lab sounds futuristic, but the concept is straightforward. A self-driving car senses the environment, makes decisions, acts, and updates its behavior. A self-driving laboratory does something similar for experiments. It uses instruments and robotics to run experiments. It uses machine learning to interpret the results. It uses optimization or reasoning systems to choose the next experiment. Then it repeats the loop. Hypothesis, experiment, analysis, next hypothesis. This loop is the heartbeat of science. For centuries, humans have performed it manually or semi-manually. Now parts of it can be automated. In chemistry, a self-driving lab might search for better reaction conditions. In materials science, it might synthesize and test candidate compounds. In biology, it might screen engineered proteins or genetic constructs. In battery research, it might optimize electrolytes or electrode materials. In synthetic biology, it might design, build, test, and learn through many cycles faster than a manual team. The reason this matters is simple. Science is often limited by iteration speed. You do not learn only by thinking. You learn by testing. And if each test takes days, weeks, or months, the discovery loop is slow. If AI and robotics can compress the loop, discovery accelerates. But here is the subtle point. Automation alone is not enough. A robot that performs a bad experimental strategy faster only gets you bad results faster. The real power comes when automation is paired with intelligent experimental design. The system must decide not only what it can test, but what it should test. That means balancing exploration and exploitation. Exploration means trying uncertain possibilities to learn more. Exploitation means focusing on candidates that already look promising. Human researchers do this intuitively all the time. A self-driving lab must encode that judgment mathematically, statistically, or through AI planning. This is where active learning becomes important. Instead of training a model once and letting it predict passively, the system chooses new experiments that will improve the model most efficiently. It asks, what experiment would reduce uncertainty? What measurement would distinguish between competing hypotheses? What candidate might fail, but teach us something valuable? That is a profound shift. Science is not only about answers. It is about choosing good questions. AI for science becomes truly powerful when it helps choose the next question. But we also need to talk about the social impact. Autonomous laboratories could democratize some forms of research. A small team with cloud models, robotic platforms, and shared data could compete in areas that once required large institutions. Or the opposite could happen. The best systems could require enormous compute, proprietary datasets, expensive automation, and elite facilities. Then power would concentrate even more. Both futures are possible. The technology itself does not guarantee openness. Access matters. Governance matters. Scientific culture matters. And as AI for science becomes more powerful, the question is not only what can be discovered, it is who controls the discovery engine. This brings us to the human scientist. Whenever a new technology appears, people ask whether it will replace humans. In science, that question is too simple. AI will replace some tasks. It will automate some workflows. It will reduce the need for certain forms of manual search. It will change what junior researchers spend their time doing. It will make some old skills less central. It will make some new skills more valuable. But the scientist is not just a machine for producing answers. A scientist chooses problems. A scientist understands context. A scientist notices when a result is too clean, too convenient, or too strange. A scientist connects measurement to meaning. A scientist carries ethical responsibility. And a scientist decides what not to do. That last point matters. AI systems are very good at optimization. But science is not just optimization. It is judgment under uncertainty. Should we design this organism Should we publish this method? Should we automate this experiment? Should we trust this model enough to act on it? Should a result be used clinically? Should a material be scaled industrially? Should a forecast trigger evacuation? These are not merely technical questions. They involve values, risk, institutions' law, and human consequences. So the scientist of the AI era may need to be more human, not less, more critical, more ethically literate, more interdisciplinary, more careful about uncertainty, more capable of working with tools that can produce fluent wrongness as easily as useful insight. There is also an education challenge. If AI can write code, summarize literature, and propose experiments, what should young scientists learn? The answer is not to avoid fundamentals. It is the opposite. When tools become more powerful, fundamentals become more important. A researcher who does not understand statistics can be fooled by automated analysis. A biologist who does not understand mechanism can be fooled by a plausible model. A climate scientist who does not understand physics can overtrust a fast forecast. A chemist who does not understand synthesis can accept a molecule that cannot realistically be made. AI raises the ceiling, but it also raises the penalty for shallow understanding. The future belongs to scientists who can combine domain expertise with computational leverage, people who can ask better questions, people who can audit machine-generated answers, people who can build feedback loops between models and reality, people who understand that the model is not the world. That may be the most important sentence in this entire episode. The model is not the world. It is a compressed representation of patterns, learned from data, assumptions, objectives, and architecture. It can be brilliant. It can be useful. It can be transformative. But reality gets the final vote. That is why experiments remain sacred. In the AI for science era, the laboratory becomes more important, not less. Because the lab is where the model's dream meets the resistance of matter. Now we need to talk about risk. Every accelerator can accelerate the wrong thing. AI for science can accelerate medicine, clean energy, climate adaptation, and biological understanding. It can also accelerate mistakes. It can accelerate dual-use biology. It can accelerate irreproducible research. It can accelerate overconfident claims. It can accelerate concentration of power in institutions that own the data, compute, and infrastructure. It can accelerate the gap between what science can do and what governance can understand. The first risk is reliability. AI systems can be wrong in ways that are difficult to detect. A model may make a prediction with apparent confidence. It may generate a plausible explanation. It may pass common tests. But in a high high-stakes domain, rare failure modes matter. In drug discovery, a wrong prediction may waste years or miss toxicity. In climate modeling, a wrong extreme event forecast may lead to underpreparation. In materials science, a predicted material may be unstable or impossible to synthesize. In autonomous labs, a flawed optimization target may produce misleading success. The second risk is reproducibility. Science depends on the ability to verify results. If AI workflows involve proprietary models, hidden datasets, undocumented prompts, changing code, and automated decisions, reproducibility becomes harder. We will need standards for documenting AI-assisted research. Not because documentation is exciting, because trust is built from traceability. The third risk is data quality. AI systems learn from data. Scientific data can be messy. Published literature is biased toward positive results. Datasets may be incomplete. Experimental conditions may be inconsistent. Measurements may vary by instrument. Labels may be wrong. Historical data may not cover future conditions. A model trained on flawed data can learn flawed science. The fourth risk is access. If the most powerful AI for science systems require massive compute, expensive data, and robotic infrastructure, discovery may become concentrated among a small number of corporations, governments, and elite institutions. That could produce breakthroughs, but it could also reduce openness, competition, and public accountability. The fifth risk is dual use. The same tools that design helpful proteins might design harmful ones. The same automation that speeds up medicine could lower barriers for dangerous experimentation. The same models that optimize chemistry could be misused. This does not mean stopping AI for science. It means building guardrails with seriousness. Scientific openness and safety have always been in tension. The AI era sharpens that tension. And finally, there is the risk of cultural distortion. Science could become too obsessed with what AI can optimize. Metrics could replace understanding. Speed could replace depth. A flood of generated hypotheses could overwhelm peer review. Researchers might chase model-friendly problems while neglecting slow, difficult, field-based, observational, or theoretical work that does not fit cleanly into automated pipelines. The goal should not be to turn all science into a machine workflow. The goal should be to use machines where they expand truth-seeking. Because science is not simply production. Science is disciplined contact with reality. So why does this feel especially important now? Because multiple streams are converging at once. First, the models are better. Large language models, diffusion models, graph neural networks, protein models, foundation models for molecules, weather models. and multimodal scientific systems are all improving. Second, the data are larger. Science has generated enormous datasets. Genomes, protein structures, microscopy images, electronic health records, climate reanalysis, satellite observations, materials databases, chemical libraries, experimental logs, literature archives. Third, the instruments are more connected. Modern labs increasingly produce machine-readable data. Instruments can be networked. Robotics can run protocols. Cloud systems can coordinate analysis. Fourth, the economic incentives are strong. Drug discovery, energy storage, semiconductor materials, climate risk, agriculture, and biotech all have enormous commercial and public value. Fifth, the scientific culture has changed. Researchers who once saw AI as a specialized computational technique now increasingly see it as a general research tool. That cultural shift matters. A tool changes science only when scientists trust it enough to use it, criticize it, improve it, and build workflows around it. We are entering that stage. Not full maturity, not solved science, but a new operating phase. AI for science may sound broad, but that breadth is the point. It is not one field. It is a layer across fields. It is like mathematics, like statistics, like computation itself. Once a method becomes general enough, it stops belonging to one discipline and becomes part of the infrastructure of knowledge. That is the long-term possibility. AI as infrastructure for discovery. But infrastructure also shapes behavior. Roads shape cities. Electricity shapes industry. The internet shapes communication. AI will shape what kinds of science are easy to do. What questions are cheap to ask? What experiments are prioritized? And what institutions gain power? That is why this trend deserves attention now. Not because every claim will come true. Many will not. Some startups will fail. Some models will disappoint. Some papers will overclaim. Some automated systems will produce noise. But the underlying shift is real. Science is becoming more computational, more automated, more model-driven, more deeply connected to AI. The frontier is no longer simply, can AI generate text? The frontier is, can AI help generate knowledge? Before we close, I want to give a simple framework for understanding AI for science. When you hear a claim about AI in research, ask where it fits in the discovery loop. There are 5 stages. Stage 1, observe. AI can process images, sequences, sensor readings, satellite data, microscope outputs, and experimental measurements. Stage 2, explain. AI can help find patterns, cluster phenomena, summarize literature, compare hypotheses, and reveal relationships. Stage 3, predict. AI can forecast weather, estimate molecular properties, predict protein structures, model disease risk, or estimate material behavior. Stage 4. Design. AI can propose molecules, proteins, materials, experiments, circuits, or workflows. Stage 5. Act. AI can connect to robotics, instruments, lab automation, and autonomous systems that physically test the design. The full revolution happens when all 5 stages connect. Observe, explain, predict, design, act. Then the result feeds back into observation. The loop begins again. That loop is the engine. And the speed of the loop determines the speed of discovery. This is why autonomous workflows matter so much. They connect model output back to reality. A chatbot can produce an answer. A scientific AI loop must produce a test. That is the difference. Science does not end with a sentence. Science ends with reality answering back. There is a temptation to talk about artificial intelligence as if it were an alien mind arriving from nowhere. But in science, AI is better understood as the next great instrument. The telescope extended sight into the heavens. The microscope extended sight into the small. The spectroscope revealed hidden signatures of matter and stars. The particle collider exposed the substructure of reality. The genome sequencer opened the code of life. The supercomputer made it possible to simulate worlds of weather, plasma, molecules, galaxies, and cells. AI extends search. It lets us move through spaces too vast for intuition. It lets us compare patterns too numerous for memory. It lets us design candidates too complex for manual trial. It lets us accelerate the loop between question and test. But every great instrument also changes the human being who uses it. The telescope changed our place in the cosmos. The microscope changed our understanding of life and disease. The genome changed our understanding of inheritance. AI may change our understanding of discovery itself. For a long time, science has depended on human imagination, pushing against the limits of human time. A researcher can read only so much, test only so many conditions, hold only so many variables in mind, run only so many simulations, design only so many molecules. AI does not remove those limits completely, but it stretches them. And when limits stretch, new questions appear. What diseases become tractable? When molecule search becomes faster? What proteins can be designed when nature's library is no longer the boundary? What materials become possible when we can screen vast spaces before synthesis? What climate risks become visible when forecasts and simulations accelerate? What discoveries become possible when laboratories can learn overnight? These are not small questions. They are civilization-level questions. But the answer will not come from AI alone. It will come from the relationship between model and experiment, speed and judgment, automation and responsibility, intelligence and wisdom. That relationship is the real frontier. If we get it wrong, we may produce faster noise, faster error, faster concentration of power, faster danger. If we get it right, we may gain one of the most powerful discovery engines humanity has ever built. AI for science is not just about making machines smarter. It is about making discovery more capable. It is about compressing the distance between ignorance and experiment. It is about giving the human mind a new instrument for entering the unknown. And that is why, in 2026, this trend matters. Because the future of AI is not only in the apps we use. It is in the medicines we discover, the proteins we design, the materials we build, the climate risks we understand, the experiments we run, the questions we dare to ask. The next breakthrough may not come from a lone genius staring at a chalkboard. It may come from a human team, a model, a robotic lab, a simulation, a dataset, and an experiment, all connected in a loop that learns. And somewhere, maybe at 3 a.m, in a laboratory where the lights are still on, a machine will test an idea that a human scientist taught it to ask. Then the data will return. The model will update. The scientist will look again, and reality will answer. This has been VTM Podcast, Episode 12. AI for Science becomes the main accelerator. I am Ralph Clayton. Thank you for listening. Until next time, keep questioning the future before it becomes the present. And don't forget, when we talk about robots or AI, I have to say this, very important. The question is not whether machines can think. The question is whether mankind will remember what thinking is for. Not every invention is progress. Not every intelligence is wisdom. Not every mercy is salvation. Build the machine. Study the machine. Use the machine. But never kneel to the machine. Because when the age of steel begins to speak with the voice of gods, one truth must remain above every circuit, every throne, and every star. Man shall remain man, or perish as himself.